x plus 3y equals 12. On those days here. Straight line. All right. X plus 3y equals 12 is going when y is 0, x is 12. When x is 0, y is 4. So something like this, first of all. Okay. And then, so now, x plus 6y equals y squared. So really, we could think about sketching maybe something you're more familiar with, like y plus 6 equals x squared. So switch x and y. So this is y equals x squared minus 6. So we definitely should be able to switch that, sketch that, and then our x plus 6 equals y squared is just going to be somewhat of the inverse graph, right? All the x and y coordinates will be switched. So y equals x squared minus 6 is going to have a vertex where? Negative 6. 0, negative 6. And then it's going to open which way? Left, right, up, or down? That'll open up because it's positive x squared. So if we think about, it's going to open up like this. So our problem, x plus 6 equals y squared, is going to have a vertex of what? If the vertex of this one is 0, negative 6, and the vertex of this one, x and y's are swapped, right? So negative 6, 0. This one opened up on the positive x-axis. So this one will open up on the? No. X and y are switched. It's not, we're not taking the opposite of things. X and y are flipped. So if this opens up on the positive x-axis like this, and this one will open up on the positive y, right? So everything with x and y is just flipped, swapped. Okay? So now this is going to come out here and intersect somewhere down over here. So notice this doesn't say anything about a region defined by an axis, x or y axis. If it doesn't say an axis, then an axis is not part of the boundary. You've got to read really carefully. Make sure you know whether or not an axis forms a boundary and which axis it is. But in this case, it's just the two curves. It's just the two curves, so axes have nothing to do with it. So we've got then that is our region between the two curves. So if we orient the strips vertically in one direction, we're going to only need to use one strip, one typical strip. We'll generate the whole region for us. If we then flip the strips and do it the other way, it's going to take two integrals. So we have to determine, oh, it's even telling us, right? It's even telling us dx is going to take 2, dy is going to take 1. Okay? So they wouldn't have needed to tell you that. You still should be able to conclude that even without given the fact that the sum of two integrals is in terms of x and the one integral is in terms of y. That was extra, that was free, right? And you could have figured that out yourself. Okay, so we'll do x first. So why does it require two integrals? Because starting, so we're gonna integrate. So if we think about, if we start over here, we get a typical strip like this, right? But then we come to a point, right, where right there, where the typical strip changes. So now over here, the bottom is still defined the same way by this curve, but then the top is defined by the line. So typical strip number 2. Okay, so we need, what do we need? We need, this is like area strip 1. And maybe this area strip 2. So we're going to find the areas of our typical elements. And so we know that area is going to be base times height. Base is dx, delta, so delta x. And then the height will be this, right here. Is that an x coordinate, a y coordinate, a change in x, or a change in y? The height of that strip. Is it an x coordinate or a y coordinate? It's always going to be one of these 4 things. Either an x coordinate, a y coordinate, or a change in x, or a change in y. Which one's that? She wants change in y. Agree with that? Yeah, because it's from one y value of one curve to the y value on another curve. So this is going to be what? y2 minus y1. And that's our area of a typical strip. Base times height, right? Base times height. So the question is, what is the y-coordinate of this point right here? And what's the y-coordinate of that point right now, right there? Well, they both relate to this parabola, right? And what was that parabola? X equals, or y squared equals x plus 6. So we need y-coordinates. How are we going to get the y-coordinate? Square root, right? Square root of both sides. But then when you do square root of both sides, you get plus and minus, and that's what gives you the 2 different curves, right? That's the 2 different curves. So y equals the square root of x plus 6. So positive square root of x plus 6 is, of course, which side of the curve? The top half is, this is y equals positive square root of x plus 6. Bottom half of the curve is negative square root of x plus 6. So when you solve that for y, you get the plus or minus. That gives you the 2 different curves. Radical x plus 6 on top, negative radical x plus 6 on the bottom. So then we got our y2 minus y1. So it's going to be y2 is going to be radical x plus 6. And it's going to be minus y1, which is negative radical x plus 6. Delta x.
Can we just put 2 times positive radical x plus 6?
Is it equal to that? Is it equal to that? Sure, when things are equal, you can write a different form as long as they're equal. That's right. But that doesn't, so that form of it doesn't relate immediately to what we're looking at, right? So that's why I'm setting it up this way, just so we can see. It's the top value of y minus the bottom value of y. We see it's the change in y. But yes, if it's equal to something else, then you can put that something else. Okay, second one then is, again, base is delta x times height is, again, y2 minus y1. But now our y2 is different, right? The y1 is the same. It's this bottom curve here, the negative radical x plus 6. But the top is, solving for y, 12 minus x all over 3. So again, y2 minus y1. But now y2 is different. y2 is 12 minus x all over 3. And then minus y1, negative radical x plus 6. So those are going to be our integrands. So this thing they're calling f of x is going to be this right here. This ends up being the function, which is the height of our typical strip. And then this function is the g of x, the height of the second typical strip. So all we need now is these limits of integration. So the first strip is going to be here at what? X equals, that's our negative 6. So we're ready to go here. So negative 6. So now we need intersections, right? So we need where x's and y's are equal. So we could set x is equal, and we get, do that in blue down here. Setting x is equal, be 12 minus 3y equals y squared minus 6. So now we have a quadratic, and we're going to get two solutions, and those are the two y values of our 2 points. So it's going to be y squared plus 3y equals negative 18, or minus 18 equals 0. So factors of negative 18 that add up to positive 3.
Plus 6, negative 3.
Therefore, this is x equals negative 6 here. And this is x equals 3. So my picture is way off. It's not to scale at all. But it's okay. We got the general gist of it, and as long as we get the numbers right in the algebra. So we're gonna go from. Wait a sec. That's not right. Something's wrong. This was negative 6, right? That intersection is the intersection actually through that? No, that wouldn't be right. Something's wrong. Something's wrong.
Intersection should be
What did I do wrong?
left, right the y got.
But this is negative 6 already. This got to be something greater than negative 6. What am I doing wrong here?
You have negative 6 for the x, and it's for y.
Well, these are y's. These are y values. Thank you. Thank you. These are y values. Okay, so these are y values. So this. Oh, so my picture may be better after all. So this is y equals positive 3. What is x equal and y is positive 3? 9, 3? Positive 3. All right, and then when y is 3, what does x equal? Sorry, negative 6. 30? All right, so my picture's not so bad, although this should be in positive territory over here. That's okay. So we're going to go from negative 6 to 3 to 30. So this one goes from negative 6 to 3, and then this one goes from 3 to 30. A to B, B to C. Okay, there's a lot of work there. Anybody have a question? So that's just the splitting it up into 2. Anybody have a question on that? In terms of going this way, I don't want to write anymore. It's going to become a mess. But going that way is actually the easier case. You're going to have, because it's just one strip. And we know now that A is going to be from, what we're going to, yeah, negative 6 to 3. So we're going to be, now we're going to be lying the strips horizontally on top of each other. So it'll be from negative 6 to 3. Okay, and so then what will the typical strip, I'll just draw the typical strip here in black. Is that height of that typical strip, is it an x coordinate, a y coordinate, a change in x, or a change in y? It's always going to be one of those 4. Is it an x coordinate, a y coordinate, a change in x, or a change in y? Change in x. So it's going to be x final, it's called x2, minus x1. And what is x2? That's the x of the line. It's going to be 12 minus 3y. Minus 6 minus y squared. So that the function that we're integrating is the height of this horizontal strip, which is change in x, or 12 minus 3y. That's the x at the right side minus the leftmost x, which is defined by that parabola. So that would be the y squared minus 6. So I think you got everything now. Then the area, solve either one. Take your pick, right? So it'd be easier to probably do the less work to do the one in terms of y, because it's just one integral and no square roots, right? Okay, questions on this example? Yes, please.
I missed the part where you got the 30 and negative 6. So I understand how you got the other intersection, but how did you get that last intersection?
So you saw how I got the y values of those points?
Yeah.
So I said x equals, and I got two y values. So I can just go back to this. So when y is negative 6, you can just use this. What is x?
Okay.
And then when y is 3, you can just use this. What is x?
Okay.
Because it's going to be, they're points on this line, so they got to make this equation true.
Right.
So just pick off those y values and get your x values right from that one.
Gotcha.
Or this, either way.
Either one.
Either one, right? They're points on both curves. So they got to make both those equations true. Other questions? Okay, what was the other one? Are we good? Was it not 9? Okay, so for this one, again, good sketch needed. So 4 sine x is going to look like this. And then 3 cosine x is going to start, so if this is 4 here, 3 cosine is going to start here. And then this is going to hit 0 there, and then a minimum there. Okay, and where is 0.8 pi? Let's see, so here is pi. So 0.8 pi is right here. So we want the area enclosed between from 0. So can we see what region we're talking about there? So between the two curves from 0 to 0.8 pi. This is pi here. And this is pi over 2. So we should recognize that we're talking about that. But then at this intersection point, things change, but it's still between the curves, and that's going to actually, in my case, for my problem, it's going to extend down below the x-axis. So, do we have just one typical strip for the whole region? So, once I find this typical strip, will it work from 0 to 0.8 pi?
No.
No, because why? Because when we do this one, we're going to have a, what is it? Change in y, right? It'll be upper y minus lower y. But they'll switch, right? Now it's different. Here, the upper and lower y switch. Typical elements. Practice that, you guys. Practice. Okay, so the red one, area of a typical strip, is going to be base times height, which is base. Delta x, height is change in y. y2 minus y1. In this case, what's y2? 3 cosine x. And y1? Typical strip number, and that's from, so and then we're going to find this x value of this intersection. We'll do that next. But then we, after the intersection, it flips. So then we have delta x equals. Now your y2 is 4 sine x. So we're going to add integrals, and we're going to need this intersection point. That's the x values that make the y's the same. So where is 4 sine x equals to 3 cosine x? Well, that's where tangent x, sine over cosine, equals 3/4. So it's arctan of 3/4. So we're going to integrate from 0 to arctan of 3/4.
Why is it 3/4?
Sine over, because I'm dividing by cosine, I'm dividing by 4. Right?
Divided by. Why aren't we divided by?
Because I want,
Oh.
you see it?
Yeah.
Okay, and then this is going to be in this first region from 0 to arctan 3/4. It's going to be the red one. It's going to be 3 cosine minus 4 sine. And we're going to add from arctan 3/4 to 0.8 pi. Now it's going to be the blue typical strip, 4 sine minus 3 cosine. And then watch your signs, your SIGNs, pluses and minuses. Make sure you have your antiderivatives right in terms of pluses or minuses. And then when you're subtracting, you're plugging in your limits of integration. You're applying negatives correctly when you're subtracting, right? So there's going to be maybe some tricky plus and minuses you got to really keep track of. Questions on this one? Yes, please.
Why didn't you include the middle part as another region, like between?
So it's between the curves, right? So as we go from here to here, as we go from here to this intersection, what's between the curves? Just this, right? And once we pass the intersection point, now what's between the curves? So this is all the stuff between the curves up until 0.8 pi. Do you see it? Yeah, sure. Other questions? Okay, so I think these two examples did a pretty good job of covering area. So there's lots of different issues we encounter with area. Last chance. Okay. It's pretty similar to the first one we did. Just make sure you have the region right. And now you can choose either way. You can figure out the way that's going to give you one integral, which I think is dy, the horizontal strips on this one. But it's pretty similar to that first example we did where they made you do it both ways. Okay. So now we get to do some fun stuff. Not that this hasn't been fun yet. It's just more fun. So today's stuff is more fun. Okay. So let's kind of summarize here. So our meanings for integrals. All right. So when we have a rate, this is how we started. We talked about rates, rate of change, and quantity and accumulation perspective. So I'm not asking for any expressions or mathematical notation here, but just meanings, right? So when we take an integral in this perspective, rate of change, accumulation, what is it that we are integrating, or what would you put in that box in your own words? What would be the meaning of what we're integrating in this context? The rate. So are we integrating the rate of change? Is that right?
Over a small interval.
But it's still integrating the rate of change.
Yes. The rate of change with respect to the change in something else.
But it's still a rate of change.
Yeah.
Ariana's the only one shaking her head. Tell me.
Change in rate of change times.
Right. It's not. We're not integrating rate of change, you guys. We're not integrating rate of change. What are we integrating? No. F of x. Dx is not just an afterthought. It's part of the math. It's part of the math. We need it. We're not integrating rate of change. We're not summing up a bunch of rates. Right? What are we summing up a bunch of? Changes in the quantity. Little changes in the quantity that we find by rate times a change in x. Dx isn't just the signal that, oh yeah, we're just tacking this on because it's integration. No, it's part of the math. This is a product. This is multiplication. This is multiplication. Really important. It's the multiplication of what? M times change in x. But it's just a really small change in x, right? So this is, then what do we get? We get a little change in the quantity. When we multiply rate times change in x plus rate times change in x plus rate times change in x as we move, as x increases, we get a little change in the quantity. Okay, so if we hadn't been sure about this in the past, know it now. We're not integrating the rate of change. We're not summing up a bunch of rates. We're summing up a bunch of small changes in the quantity, which we get by rate times a change in x. Okay? Remember, if you're going 60 miles per hour on the highway and you go for 10 hours, how far do you go? 600 miles, right? You just did m times a change in x. 60 miles an hour times 10 hours gives you 600 miles. Okay? And what do we get when we do that? So we're going to sum up a bunch of little changes in the quantity, and we're going to get what? What's that?
Accumulation of changes.
Okay? An accumulation of changes, right? Or a total change. So we're summing up little changes in the quantity, we get the total change in the quantity. All right, what about, now so let's, with area perspective. What is it that we're integrating, and what do we get? Why don't you discuss this with the person next to you? So when in the area perspective, what is it that we're integrating, and what do we get? Go.
Like you said yesterday, that area is just a byproduct of the way we use the
Untitled Chapter.
So it's the little change in base times high.
Could be wrong. Probably wrong.
And then
Gamble that one in math and science. Probably wrong.
Okay, so what are we adding up in the area perspective? What is it that we're integrating?
Little bits of area.
Okay, right, exactly. So this is a little bit of area. Specifically, area of a rectangle, right? A really thin rectangle. And what do we get? No. Oh yes, sorry, exactly. Yeah, so we're going to get difference of areas, right? Difference of areas. Or kind of like a total net area. Nothing to do with accumulation, right? So net area, difference of areas. Okay, so similarly, we're going to take the volume perspective. So when we have volume perspective, this should kind of fall out in place here.
Bits of volume.
Yep, little bits of volume. We're going to calculate a little bit of volume, and then we're going to add up those up. To get total volume. Okay, so yes, it was net area when we just looked at a function and we let it go up and down above and below the x-axis. But in these problems where it had us construct a region, remember, so we had a function and maybe use the x-axis, we constructed a region. We were really finding the total area of the region, right? Whether that was above or below the x-axis, we forced our strips to be positive areas the whole way, so that we got the area of the region. So really, what I'm talking about here is total area. Okay. If you just integrate a function that goes up and down above and below the x-axis, yes, you get difference of areas with the x-axis. But when we're talking about a region and we want to get the area of that region, we can talk about it truly as area. Okay. So, where do these volumes come from? All right, so here's an example. Find the volume of a solid formed by rotating r around the x-axis, and r is the region formed by y equals 0, y equals x squared, and x equals 8. So I want you to sketch r first. No calculators. Sketch r first. Got to get this right. Forget about rotating. Just sketch R. Just ignore the rotating part. Sketch R. We need a good sketch of R. Don't forget the rotating. For now. If you started, you can leave it. Let's see that you can sketch R.
Unless you want it all the time.
Don't have R. We gotta get R. Gotta get the region R. R is a two-dimensional region. Show me. No. Yeah, but you're not showing the whole thing. So the region has boundaries on all sides, right?
Goes from y equals. Oh, it's.
Gotta get R, so it's gotta get a good sketch of R. No. Still trying to rotate something. I don't care about rotating. I want to know what R is. Just look at the second sentence. That's right.
Sorry.
That's right. That's right. That's right. That's the region.
Just make your before, yeah, like your graph. That's what it's.
Go to here. Go to here. The parabola is only going to extend to 0.8.
What's the region?
So it's this. Oh, it's this whole thing out to. Nope.
What is y equals 0, Joseph? Y equals 0. What does that mean? Yep. Most of us are given now. Okay, this is what it looks like. At least half of us got it. All of us should be able to get that. That's a pretty easy region. So y equals 0 is not the y-axis, right? What is y equals 0? It's the x-axis, right? Values where y is 0 would be on the x-axis. We're not going up or down, right? So that's the x-axis. So this is the region. Okay, are we good on that? Everyone, any questions? So now what did it say? It said we want to rotate that about the x-axis. And when you rotate that thing about the x-axis, all the points in space that get hit by that region form a solid. Do you see that? Can you imagine what that solid will look like? Not like a spinny thing. A solid thing is a solid. So it's like that. It's like a Hershey's Kiss, right? Also just move it. Okay, so when we rotate that thing about the x-axis, we get this curved cone thing. Okay, so how are we going to go about doing this? So we're gonna approach it the same way that we approached the other things. We're going to go for a typical element. And so the typical element is going to start by our what happened? Oh, that's still view 2. Okay. We're going to start with a typical strip, right? We're going to start with a typical strip. And we're going to say, when we do that rotation, what do we get? What does the typical strip form in that rotation? So what kind of thing do we get when we take the typical strip around the x-axis? What do we get? So when we rotate the typical strip around the x-axis, we get someone said a circle or a disk. So circle is a two-dimensional object. This is three-dimensional now. So it's a disk, or I like to call them a pancake. It's a pancake, right? Standing up on its end. And so then what we're going to do is, if we want the total volume, it's going to be the sum of little volumes. And those little volumes are going to be these volumes of these pancakes. So we imagine then that then we're going to add together a bunch of pancakes. So when we starting at here 0 and ending at 8, we're going to add together all those pancakes, and then that's going to form that solid that I showed you back here. So in the region, we form the typical strip, and we rotate that typical strip just like we're rotating the whole region. That forms a pancake, and then we're going to add up all those pancakes to get the. So there's the one pancake. We're going to add up all the pancakes from left to right, and make those pancakes really, really thin, and we'll get the volume of the solid. Does it make sense? Okay, so we got all the tools, we can do it. So if you had, before I told you to, if you had drawn this picture, as I saw some of you had, that's good. Something like that. So we're going to have, again, we're going to have our typical strip. When that gets rotated around the x-axis, that forms a typical pancake. Yeah. Okay, so what do we want? We want the volume of a pancake. And then we're going to sum all them up. So what is a pancake? What is a pancake? Essentially, in geometry, what is that?
Very short cylinder.
She wants a very short cylinder. Hunter likes it. Jacob likes it. Alvaro. Yeah, that's what it is. It's a cylinder that's just really squat, right? It's just a really squatty cylinder. So what's the volume of a cylinder?
It's a circle.
Circle, pi, or squared, h, right? So before we did the area of a rectangle, when we rotate that rectangle, we get a pancake. So now our typical element will be the volume of a pancake. So what is the radius of our pancake? Is it an x coordinate, a y coordinate, a change in x, or a change in y? The radius. So again, remember where that came from. It's this thing rotated about here. So the radius is from here to here is the radius. So x coordinate, y coordinate, change in x, change in y. Just a y coordinate. So yeah, a y coordinate you can think of it as a change in y, but more simply, it's just the y coordinate. Do you see that? Because it's the distance from the x-axis up to the y here. You see that? That is the y coordinate. Sorry, I should have made that bigger. So the radius is just the y coordinate. And what about the height of the pancake?
Change in x.
That's a little change in x, right? So if we got a little change in x, now we got to write y in terms of x. So what is the y coordinate in terms of x? Y is just x squared, right? So the volume of our pancake is pi y squared, or x squared squared, delta x. Okay, and then, so that's our setup work. So then the total volume is going to be volume of the kiss, Hershey's Kiss, is going to be, we're going to sum up all the typical pancakes. From what to what? Yep, the first one is going to be right here at the origin at x equals 0. The last one's going to be at x equals 8. So 0 to 8, pi, x to the fourth, or x squared, I'll just do x squared squared, dx. Easy integral, super easy integral. Questions on this first example? Talk to me.
I got it.
So what were you, just go ahead and say what you were thinking.
I realized it didn't make much sense because we have because y is 0. So I was wondering why is there not a difference of two formulas, but y is 0. So
Yeah, so in if you're looking at this typical pancake, here comes the x-axis right through the center of it, right? Because our strip went from the x-axis up to the curve, and then we rotate that strip around the x-axis. So then that radius is exactly just the y-coordinate, which is a change in y. It's y minus 0, but more simply, it's just that radius is the y-coordinate. Other questions? Okay, let's try this. So same region. Try a little bigger this time. And we're going to rotate that about x equals 8. I'm going to rotate that about x equals 8. So what is x equals 8? Is that a vertical line, horizontal line? What is that? Vertical or horizontal? Vertical. It's this line right here. It's the bound. It's actually x equals 8 forming the boundary, right? That's this line right here. So I'm going to take that same region, and rather than rotate it about the bottom boundary, I'm going to rotate it about the right-hand boundary. So first of all, what will I get this time? Like, yeah, another Hershey's Kiss. But this one's going to be like that first one was like really wide and not very tall, because this point is what, 64? This 864. So now this one is going to be like a spire, right? It's going to be the same general shape, but it's going to be like a spire, and it's going to be pointing up instead of pointing left. Something like that, and we're going to rotate about it this way, so it's going to look like this. So what are we going to do here? So our typical strip is going to be vertical or horizontal. We want to get pancakes. And now we're going to use a horizontal typical strip. And to get our typical element, we say, okay, we're going to rotate the typical strip about the line x equals 8. And when we do that, we're going to get pancake. All right, so we want, again, what the area of a pancake. Area of a pancake is still a cylinder, pi r squared h. So when you use pancakes, you'll always, your area will always be pi r squared h, just like strips are always rectangles. Strips will always be b times h, so area of the pancake will always be pi r squared h. Okay, let's do our height first. That's the easy part. What's the height? Change in y, right? The height is a little change in y, so delta y. Okay, now the radius. Is it x? So the radius would be from what?
H minus x squared.
So is it a change? Is it an x coordinate, a y coordinate? Change in x or change in y? That's the radius right there. Do you see it? The radius is from the center of rotation, x equals 8, out to the curve y equals x squared. So what in general is that?
8 minus
8 minus x squared.
Change in y, change in x or y? Change in x. So it's going to be x2 minus x1. So lots of you you're saying correctly what it will be. I just want to do every step, okay? So that radius is a change in x, right? So it's going to be a final x. And what is x2? 8. For every pancake, for every single pancake, the rightmost is 8. And what is x1? Careful. It's x1, right? Oh yeah. Okay, so yeah, so we need to get these all in terms of y. So it's the x coordinate of that, which in terms of y is the square root of y. So there's our setup work. We got our typical pancake. Oh, sorry, volume. Did I write AP before or VP? I did write VP before? Yeah, it's V. It's not A, it's V. Okay, so now we want the total area. Jeez, volume equals. So we're going to stack up all these pancakes starting at y equals 0 until y equals, the last one's at 64. Easy. Right, after our week of all these hard techniques, we dive for integrals like this, right?
So how hard will the holdup be?
Oh, we're gonna do harder problems than this. These are easy ones.
Oh, I didn't know.
Oh yeah. Okay. Questions on this? Anybody have a question? All right, so. Oh, lucky you. We get the same region again. And now we're going to rotate about the line y equals 70. So, sketch it out again. Sketch the line y equals 70. And then do your best to sketch the solid that we're going to get. See if you can come up with what. So sketch the region, sketch the solid. So where's y equals 70? Where's y equals 70? This? Higher, but what is...
Slightly higher, like a ball that has a bit of a.
So y equals 70 is this right here, something up here. Now we're going to take that region, that same region, and now rotate it about y equals 70. So you can kind of like do a point at a time. So when you rotate 864 about y equals 70, when it's halfway around, where will it be? Like there, right? And then this point, when it's halfway around, something like this. And then this point at the origin, when it's halfway around, something like that. So when this thing hits 180 degrees, halfway of rotation, we're going to get this image here. But it's gonna pass through all points in space along the way, and what are we gonna get? Can you imagine it or explain it? Yeah, good. So it'll be a bowl standing up on its side with a hole in the bottom. So let me try to draw it here. That. Oops, sorry. I can do better than that. There we go. But then there's also this. Something like that. So this is okay, that's a good one. All right, so I'm going to take my typical strip here. And again, to get my typical element, I'm going to rotate that about the same line that I'm rotating the whole region about. So at 180 degrees, it's going to be up like this. Yeah. Yeah.
That hole in the bottom of
Mhm.
the bowl, whatever it is the bottom of that y equals 64 and the top of it y equals 70? Is that what that is? Is there a hole?
No, the hole is here, right? The hole is here.
Okay.
Because imagine this thing is rotating about y equals 70. So this is the hole right here.
So then it would be 64 and 76.
Yeah, so we don't, we're,
Just so I understand where the hole is.
yeah, the hole would be, yeah, if we were superimposing it into the plane, it would be from 64 to 76.
Okay.
Yeah. So now our typical strip to get we need an element of volume that we're going to have a typical element of volume. So we start with a typical strip in the region and we do that same thing with it that we did with the whole region. We rotate it around y equals 70. So here's where that is at 180 degrees of that rotation. So what do we get a pancake?
No.
What do we get? If we don't get a pancake, what is that? So imagine this strip rotating about y equals 70. So what do we get?
It's like a really thin, a really skinny donut.
A real skinny donut, flat, a flattened like a donut that's been run over.
A wafer.
Which it's like it's a washer or wafer. Yeah, it's like a wafer with a hole in it. So it's like a pancake, but it has a hole in it. So that's our typical element, and we call it so. We call that a washer. So we're going to do the volume of a washer. So before we get into the specifics of this problem, how, just in general, any washer, how would we structure or how would we think about getting the volume of a washer? Yeah, William. William, go ahead.
Just the volume of the big circle minus the volume of the little circle.
Circles?
Or cylinders.
Yeah, so yeah, it's going to be the volume of big pancake minus little pancake. Right? So it's going to be the volume of the whole thing, like the big pancake, minus the whole. So yeah, volume of the, so say H. Volume of the pancake minus the volume of the whole. And that gives us the volume of the washer. So, and those are both so we'll call those are both themselves pancakes, right? The whole thing is a pancake. That hole is the shape of a pancake. So it's going to be pi r squared h minus pi r squared h. Now we're ready to start figuring out what these things are. So let's start with the height. That's easy, right? What is the height? The height of the washer.
Delta.
He wants delta x. Agree with that? Yep. So delta x, delta x. All right. And so then, what is the radius of the outside pancake? So the radius would be what? From the outside?
Yeah.
That's r sub p. Looking back at our situation here, what is that? So that's from the outside of the pancake to the center of rotation. What is that radius?
74 times 2 plus 12.
No. It's just from here to here. See that?
It'd be 70 minus x squared.
70 minus x squared. No, so where is it? It's from here to here. For all of them, right? They all start, all those, the end of all those pancakes is here on the x-axis. It's just what? Just 70. Do you see it? It's just that y-coordinate from the outside of the pancake to the center of rotation. Okay, now what about the radius of the hole? So the radius of the hole, I'll do it in blue, would be from
70 minus x squared.
So that's R sub h, what I'm showing in blue. An x coordinate, a y coordinate, a change in x, or a change in y? That radius. An x coordinate, a y coordinate, a change in x, or a change in y? Change in y. It's a change in y. So it's going to be y final minus y initial. What is, or y upper minus y lower? What is y upper? 70. The y coordinate of this curve is the bottom of the hole. The y coordinate of the curve, x squared. Okay, so we got, there's our setup. We've got the volume of a typical washer. So total volume is? Integral from? So where's the first washer? We got delta x, so the first washer is at x equals? 0, and the last washer at 8. So from 0 to 8, pi times radius squared, I'm just going to factor out the delta x, minus pi times inner radius, or the radius of the hole, dx. Another easy but a little more cumbersome integral, a little more tedious. More to do there. No, actually, that becomes very easy. Okay, question. So this is a variation on pancakes. When you rotate your strip and it makes a hole, then you have a pancake with a hole in it, which we call a washer. So then you got to do the volume of the whole thing minus the volume of the hole, and so the washer will always have, your typical element will always have this form for the volume of a typical element. Anybody have a question? Ready for another one? Last chance in our race. Let me see here.
Oh shoot. Oh, I lied. Yeah. Yeah, I was like, oh shoot. Yeah.
I thought you were saying.
Oh no, I'm saying nothing for right now. I don't know. Zero. Wait.
Because that's just
do we do? Illustrator. Why is that so hard?
So this was kind of like.
There we go.
Oh, okay. Okay, because I drew my strip, and I was thinking, so it's, okay, so it's this line here, minus the same. Oh, yeah, this line.
Yeah.
That one's ours.
That's one. Well, I did the other one.
I am
Is
like,
that? I used to take the top. But
it is top, or the writer knows. Top, stop. Okay. Right. Right on the other side.
So, could you guys do it?
Trying to find the line.
Yeah, we're trying to find wash. You guys find
Alright, and this is what I think the big
Basically, so like this interval represents this entire yeah. And then I'm subtracting. I did my points here, so I'm subtracting from this. Look at another essentially. No, this was correct. Yeah, from the x equals 9 to the linear part, and then once we get to y equals 2, x equals 9 to so that'll give it, while it's in two parts, that'll negate this entire little weird bowl cone thing in there, over top of the volcano. Yeah. That'll be a sort of surround.
Okay, find the area.
Okay.
Based on,
I saw yours.
I don't have the line before it. Let's say we're trying to figure out
You probably had a 9 here.
according to this,
So I'm like, what was it? Yeah, so then you got Westford.
seems reasonable. That probably works there.
We'll see.
So
Yeah,
it's all-
was it 7? Then that's why it went. You read it. Is that okay? And because 11 is here. Well, I mean, something you can have x equals 7 here.
Right.
So that's gonna be it. So that's not fine. Well, I was thinking that's what's coming in, and it's coming up in the.
Okay, how we doing? Any questions?
Oh, okay, that's
You done? What'd you get for the outer and the radius of the pancake, the outer radius?
Brutal when they give you sinusoids.
What's up? Yeah, absolutely. Y squared.
Oh, yeah. And then if you're strict in the first one, so you get like helices,
Plan it out.
disc washers, so
Outside radius.
Yeah.
Yes,
It's
crazy.
always gonna be 9
So.
minus 6
Radius.
Okay, so.
Look at how I see how I've drawn the washers, the strip. Just rotate the strip around, that gives you the washer. So, the radius of the strip. It's not why minus y1. We don't say y2 minus y1. Good, but it's going to be really, really small. Draw the washer and find the volume of the washer.
How did you get the
You get the draw the washer and find the volume of the washer. You don't have to think about the solid. It's on the washer.
nine?
That's not part of the volume of the washer. How are you going to find the volume of the washer? How do you find the volume of the washer?
So imagine minus
Y squared.
we're trying to cut the other radius 9 minus
Y squared. Two squared.
square root of 6 minus y minus 0 minus.
It's a subscript.
We're trying to find the other concept.
It's a subscript. R sub
And
P.
find to get
Pancake radius. Pi r squared h.
r
So it looks like you have to do this.
9 minus. You can see
So that's why zero, right?
To get the
So
big
radius.
one.
9 minus.
P is really big, so I'm wondering.
That and that's the whole.
No,
And then 9 minus y squared, it's
Yeah, but it's so big that it looks like a variable.
The first one I just wrote that.
So you take the whole thing minus this thing.
It looks like to me like you wrote R times P.
Then the second part minus.
I just want to make sure that's not what you're seeing.
And then that,
Okay, so I just want to make sure that the way you wrote it, someone else reading that would think it's R times P.
And then this first portion, minus
P is so big.
very large. Yeah.
oh, you
Someone else
will.
writing that would think, I would think that's RP squared. That's what it looks like.
This is
Anyway, so
9
you-
minus
you have
y
it
squared.
right.
Because
So what is that?
it's
to
r
get to
squared
another one.
minus
Okay, what's this?
9 minus 6 minus y.
So you see, you don't need this.
It's 9 minus 6 minus y whole squared. Because that's the radius of the inside. What are you doing? 9
That's why 9 minus
Between that,
6
we have
minus y.
and that's the
That's what the 6 minus
that's the that's the radius of the hole.
At first I put x,
So if you look at my,
Tell me
radius.
first,
when you rotate.
Okay, so this is the setup right here for your typical pancake. Okay, your typical pancake, or washer, sorry, typical washer. So here's the setup. So we're gonna find the volume of the pancake, that's pi r sub p squared h. So imagine there was no hole in it, right? It'd be the whole volume, minus the volume of the hole. Right? Just like in the last example. So we need each of this radii. We need the radius for the pancake, which is from here to here. See that? From 9 to the outside of the washer, which is on this curve. Do you see it? So what is the radius of the pancake? 9 minus this x coordinate, right? 9 minus this x coordinate. Change in x. 9 minus x. And that x is y squared. So that radius is going to be 9 minus x squared. Sorry. And the height is delta y. Okay? Minus the hole. So the hole has a radius of what?
9 minus for one part.
So that the radius of the hole is going to be 9. Again, a change in x. Final x, 9 minus, so that's the radius of the hole. So 9 minus the x coordinate on the line. X equals. So make sure we get our negatives right here. So it's 9 minus the quantity, 6 minus y. It's 9 minus x, and x is 6 minus y squared delta y. So that's the hard part of the problem right there. Getting the volume of that washer. Questions? What portion are you missing?
So, like after the line has crossed the region, we need to keep.
We're stacking up washers. The first washer will be
Oh, okay. Yeah,
here.
no, I see it now.
Stack them all up. The last one will be at this point right here.
Yeah.
So this is typical for all the washers to get the whole volume. See? Questions on the volume of the washer? So this is a hard one. So you'll be glad to know this is a hard one. This is not an easy one. All right. Therefore, total volume is. So the first washer is at y equals what?
0.
At the bottom. And the last washer is at y equals
2.
whatever the y coordinate of this is. Some people are saying 2. Y squared equals y plus 6 minus y. Y squared plus y minus 6. Y plus 3, y minus 2. So this is y equals 2. Those who said 2 have it. And then what we're going to sum up the volumes of all the washers as you go from 0 to 2. So we could factor out pi if you want to do that. Factor out pi. And then you get 9 minus y squared. Oh, sorry, this is squared. Squared minus 9 minus quantity 6 minus y squared. Did I get everything right? Pi r squared h, pi r squared h. Okay, if you had to do that by hand, multiply everything out, combine your like terms, easy antiderivative. Okay, so pancakes and washers, pancakes and washers for dinner. See you tomorrow.